During the last lecture, I introduced the index form, and I presented a corollary which says that if gamma is a unit speed geodesic which is minimizing, then the index form evaluated at every proper normal vector field along gamma is non-negative. The first result I will present today describes the relationship existing between the minimizing properties of a geodesic and the presence of conjugate points. Precisely, this theorem says that if there is an interior conjugate point, then we can find a proper normal vector field X such that the index form evaluated at X is negative. Consequently, as a consequence of the corollary I mentioned before, we get immediately that gamma is not minimizing. So let's see the proof of this theorem. So suppose that the geodesic is defined on the closed interval AC, and suppose that gamma B is conjugate to gamma A with B in AC because it's an interior conjugate point, so B belongs to the interior of this interval. So this means that there exists a non-trivial Jacobi field J along gamma such that J at A equal J at B equal to 0. So now we introduce an auxiliary vector field V along gamma writing this way. So V of T is J of T for T in AB, and it is equal to 0 if T belongs to B to C. This vector field is proper because J at A is 0 and V at C is 0. It is normal because this Jacobi field is normal, and it is piecewise smooth. Now I want to construct another vector field along gamma having the following properties. It is smooth, proper, and normal. Precisely, we write WB equal the jump of dTV at t equal b. This definition involves the use of a smooth bump function, and it gives origin to a non-trivial vector field along gamma, because dt j b is not zero. It is clear that this is equal to minus the jump of dTV, and this is non-zero, because otherwise, by the theorem of uniqueness of Jacobi fields, we would have that J would satisfy JB equals 0, dtJB equals 0. This would imply that J is identically 0, and this is not true. So W constructed this way is not identically 0. Now we are ready to produce the vector field which appears in a statement of the theorem. So if epsilon is a small positive real number, then we introduce x epsilon as a v plus epsilon w. Let's compute the index form at the x epsilon. This is v plus epsilon w, v plus epsilon w, and this is equal to 1vv plus 2 times epsilon 1vw plus epsilon square 1ww. This formula follows immediately from the bilinearity of the index form. So we know that V satisfies the Jacobi equation on AB, because on AB V coincides with J, which is a Jacobi field, and also on BC, because on BC V has been defined to be equal to 0. And we have also that V at B is 0. So then we can use the index form formula involving the Jacobi equation. So precisely we have that this is formula I. Let's write A B equal minus the integral from A to B of dt square A plus R A gamma prime B dt plus dt A B t equal A t equal B. Minus sum on I from 1 to k minus 1 of delta I dt V, sorry, dt A B AI inner product. So this is the formula 10.24, where for your convenience I replaced V and W by A and B, because we will use it for computing these three terms. 1, 2, 3. So if we use this formula, you can compute 1 VV equal to minus delta dt VB, and this is equal to 0 because this is 0. And you have that this term is not here because, as I remarked before, V satisfies the Jacobi equation. What about 1 VW? 1 VW is equal to minus delta dTV WB, but this is equal to this, so this is just a minus length square of WB, and these remain as it is. So this implies that 1 x epsilon is it equal to 2 epsilon length of WB square plus epsilon square 1 WW. And it is clear that if epsilon is enough small, the dominant term is this one, and it is a negative. So this is the end of the proof, because we constructed a vector field along gamma such that the index form is negative, and this implies that gamma is not minimizing, because we know that the sign is negative. What about the converse? So we proved that if there is a conjugate point in the interior, then the index form becomes negative, and gamma as consequence is not minimizing. So the converse is if gamma is not minimizing, it is true that there is a conjugate point. The answer is no. What is true is a partial converse of this, and in order to prove it, I need a technical lemma which says that if gamma is a geodesic segment, and J1, J2 are Jacobi fields along gamma, then the function dt J1t multiplied by J2 minus J1t multiplied by dt J2t, this is a constant along gamma. If you want to prove this lemma, what you have to do is to define a function f setting f of t equal to this function here, and we have to show that the first derivative is identically zero. The proof of this identity requires the use of the Jacobi field, the Jacobi equation and the symmetries of the curvature tensor. I leave the details to you. Instead, the theorem I want to prove says that if gamma is a unit speed geodesic segment, without interior conjugate point, then if V is any proper normal piecewise smooth vector field along gamma, then we have that 1VV is non-negative with equality if and only if V is a Jacobi field, and this says that in particular if gamma B is not conjugate to gamma A, then the index form is strictly positive. The proof of this theorem is long, but anyway we will try to present it. So in order to simplify the presentation, I will suppose that A it is equal to 0. Otherwise we can make a translation replacing t by t minus A. We set P to be gamma 0, and we denote by W1, W2, Wn an orthonormal basis of TPM. And we make a special choice for W1. Precisely, we want W1 to be gamma prime at 0. Then we define for alpha equal 2, 3, n, J alpha as the unique normal Jacobi field such that J alpha at 0 is 0 and the covariant derivative along gamma at 0 is W alpha. Since there are no interior conjugate points, then we have that J alpha t is n orthogonal basis for the orthogonal of this space in T gamma T M. The reason why this is true is that this condition, this hypothesis, implies that no linear combination of J alpha T can vanish for T in 0B. So from this observation, we get that the vector field along gamma V, which appears in the statement of the theorem, satisfies this identity, where I'm using the Einstein convention, and the V alpha are functions on 0B. Sorry, this should be R. And since V is a normal, alpha runs in in the set 2, 3, n. There exists an extension of these functions on the entire closed interval 0B. In order to see that, let's first show the extension at t equals 0. This is done using the Taylor series and the expansion in normal coordinate of J alpha. So suppose that x1, x2, xn are normal coordinates centered at P, determined by the bases W1, W2, W3, Wn. This means that if T is a positive small, we have these formulas: J alpha T equal T times delta over delta x alpha, with alpha of course equal to 2, 3, n. and consequently we have also a formula for V, because V is equal to this linear combination. So this implies that V of t is T V alpha T delta X alpha gamma T. Now we know that V is smooth on 0 delta with delta small and positive, and we know also that V at 0 is 0. Then you can use a Taylor theorem and you can prove that the components of this quotient extends smoothly to 0 delta, and this implies that this function is smooth on 0 delta. So this is the proof of the extension of the alpha to right neighborhood of 0. And in a similar way, from the fact that V at B is 0, you can prove that V alpha extends on left neighborhood of B. Okay, now let's go back to the mainstream of the proof. So if A0, A1, AK is an admissible partition for V, then this means that V restricted to AI minus 1, AI, this is, sorry, this must be open, this is smooth. On these subintervals, I can define X equal V alpha dt J alpha and Y equal V dot alpha J alpha, where dot means the derivative with respect to t. Clearly, the covariant derivative of V along gamma is equal to X plus Y on each subinterval of this form. And it is clear that since V is piecewise smooth, then dtv x y extend smoothly on the closed interval ai minus 1 ai for each I. Now what we want to do is to compute the index form at V. In order to do this, we use this identity. Length of dtv squared minus 0,4 Riemann tensor evaluated at V gamma prime V. This is equal to d dt inner product of V and X plus length of Y squared. So we will prove this later. So we will suppose that this identity holds true. Then if we use the formula for the index form involving the Jacobi equation, the left-hand side of the Jacobi equation, we get the integral from ai minus 1 to ai of dt length squared minus Riemann tensor evaluated at V gamma prime V dt, and I have to sum on k, sorry, on I, with I running from 1 to k. We have no other contributions because V is piecewise smooth. If this formula is true, then this can be written as sum on I of this term plus this other term. Where the boundary terms are to be interpreted as limits from above and below. Okay, now we observe that X and V are continuous on 0B, and this means that the boundary terms involving t equal a1, a2, ak minus 1 all cancel. So no contribution involving a1, ak minus 1. And since v at 0 is equal to vb and this is equal to 0, then we have no contributions involving t equals 0, t equal b. So this means that only this is only this term survives. So this means that this is non-negative. And what can we say if we have equality? Equality implies that y is identically 0 but what is y? Y is v dot alpha j alpha. So since these are linearly independent, then we have that this is identically 0 for each alpha, implies v alpha constant. So V is a linear combination of Jacobi fields with constant coefficients. And this says that V is a Jacobi field. This is the end of the proof, up to showing that the identity we used before is true. So we want to prove that length of dtv square minus this Riemann tensor is equal to this derivative plus this term. The starting point is to look at the derivative of this inner product, and by compatibility with the metric we get this formula. Clearly this is equal to x plus y comma x plus v dtx. This identity follows from the definitions of x and y, because x plus y is equal to dtv. So now let's look at this term. So dtx, this is v dot alpha dt j alpha plus v alpha dt square j alpha. But we can use the Jacobi equation, and we can write this as v dot alpha dt j alpha minus b alpha rm, sorry, rj alpha gamma prime gamma prime. Here there is a sum on alpha, but v is v alpha j alpha, so this is equal to v alpha dt j alpha, sorry, v dot alpha dt j alpha minus r v gamma prime by linearity. As a consequence, dtx inner product v, which is this term, it is equal to v dot alpha dt j alpha. I should write here v, but v is given by this expression that I will use after changing the index. So I write v beta j beta minus rm v gamma prime v. So this comes from this after multiplying by v. Now it's the moment of using the technical lemma which precedes the theorem. So we have the following: dt j alpha j beta inner product minus j alpha dt j beta equals 0 at t equals 0. Previous lemma implies equality for any t. So so this means that this term can be written as follows: v dot alpha dt j alpha comma j beta I forgot v beta j beta. This can be written as v alpha dot v beta. Sorry, I wrote the index on the bottom. Instead, it should be on the top. So I have this. This follows from this bilinearity. Then from this formula I get v dot alpha v beta j alpha dt j beta, and this can be written as v alpha dot j alpha v beta dt j beta. But this is exactly y, and this is exactly x. So now I will replace this formula into this formula that I will going to recopy. So instead of writing this term, which is this, I will write just yx. And now I have to replace into the formula for ddt inner product of Vx, precisely x plus yx plus v dtx. I made a typo, this is v, sorry. So I can replace this term by this one, and I get ddt vx equal x plus y x plus yx minus rm v gamma prime v. And it is done after we observe that this is equal to length of x plus y squared minus length of y squared minus Riemann tensor evaluated at v gamma prime v. Essentially, to pass from these two terms to these two terms, you have to sum up and subtract length of y squared and this formula is equivalent to dtv square minus rm v gamma prime v equal dt vx plus length of y squared. And the reason is that by definition we have that dt v is y plus x, so this term is exactly length of dtv squared, and it is done. Now we are ready to summarize what we proved. We proved two theorems. The first one says that if gamma has an interior conjugate point, then it is not minimizing. We proved also that if gamma has no conjugate point, then for every proper normal variation capital gamma of gamma then the gamma is minimizing, and this means that the curve gamma s is strictly longer than gamma, at least for s small enough and non-zero. And we proved also that if gamma A is conjugate to gamma B, but gamma has no interior conjugate points, then for every proper normal variation capital gamma, the curve gamma s is strictly longer than gamma, for s different from 0 small for all. Unless the variation field of the variation capital gamma is a Jacobi field. These three statements are immediate consequence of what we proved today. Maybe I could tell you more about this condition, the number 3, the fact that we wrote unless the variation field of gamma is a Jacobi field follows from the second theorem I proved today. Precisely, we proved that that the Jacobi field implies that I v is 0. It follows from here. And if you have a 0 for the index form, you cannot say that the length of gamma s is longer than the length of gamma, strictly longer. And now it is time to convince you that the converse of the first theorem I proved today is not true. Which is a theorem 10.26. Essentially, it says that existence of interior conjugate point implies gamma non-minimizing. So it is true that if geodesic is non-minimizing, then there is an interior conjugate point. The answer is no. It's easy to understand why if we look at this example. Consider M equal S1 times R with G equal the metric, the product metric, that is d theta square plus d x square. Then you can prove that there are no conjugate points along any geodesic. But it is clear from this picture that if you fix a point and you consider this kind of geodesic, horizontal one, then non-geodesic segment which wraps more than halfway around the cylinder is minimizing. In order to understand what happens, we have to introduce new definitions. We will work in the following setting. We will suppose that the Riemannian manifold is complete and connected. Suppose that P is a point of M and V is a vector in TPM. Then we define the cut time at TV as follows. This is the supremum of B positive such that gamma V restricted to 0B is minimizing. Of course, gamma V is a geodesic starting at P with initial velocity vector V. It is clear that T cut PV is a positive number. This is consequence of the fact that gamma V is always minimizing inside a geodesic ball of small radius. And it is clear that it can be infinite. So T cut PV can be equal to plus infinity. If the cut time is finite, then the cut point of P along gamma V is given by gamma V evaluated at the cut time. There is one more definition. The cut locus of P, denoted by this symbol. This is the set of all Q in M such that Q is the cut point of P along some geodesic. It is clear from the definition that the cut point of P along gamma V coincide with the cut point of P along gamma lambda V with lambda positive. So this means that we can work with vectors of length 1, and consequently we can apply one of the theorems we proved before today, precisely theorem 10.26, which is about unit speed geodesic segments. This implies that the cut point, if it exists, occurs at or before the first conjugate point along every geodesic. Theorem 10.26 says that geodesic segment is not minimizing if there is a conjugate point. So the cut point occurs at the first conjugate point or before. In general, it is difficult to determine the cut locus because you need to know how the geodesics, all the geodesics which originate at a point behave. There are two examples where it is instead relatively easy. The first one is SNR with the round metric. Then the cut locus of P with P arbitrary. This is just the antipodal point. It is clear this is the image of pi r and pi r is the supremum. Let's write the definition again maybe. Pi r is T cut PV because this is the supremum of B positive such that gamma V restricted to 0B is minimizing. Another example is given by SNR times RM with the product metric the cut locus of the point Px with P in SNR and X in Rm is given by minus P times Rm. We can understand why this is true in this special case. At least intuitively. So if n is equal to m and it is equal to 1, the manifold is a cylinder. Then if you fix a point Q, we know that this geodesic stops to be minimizing after wrapping halfway. So this means that if we look at this geodesic, the cut point along this geodesic is this. But there are other geodesics to be considered. For example, this one. Sorry, no, I made I made a wrong picture. There are other geodesics to be considered. They are these: helices. And you get, if you look at this geodesic, you get this point. If you take this geodesic, you will get this point, and they are all aligned. So you get that the cut locus of Q is this entire line. So if you write Q as Px with P in S1 and X in R, you will get that cut locus of Px is minus P times R. Next time we will present the properties of the cut times and the relations existing between the existence of conjugate points and minimizing properties of geodesic segments. Thank you for watching.